welcome to another episode of AI Research Today. I'm your host, Aaron, and yet again, today I'll be going through another recent AI research paper I found interesting for several reasons, and as usual, I'll put the link for the paper in the episode description. So, that being said, the paper itself is titled Meta-RL Induces Exploration in Language Agents. This was out of ETH Zurich and a couple of other research institutes. And it's an application of reinforcement learning in the agentic framework. So that we've covered a couple of papers that have discussed how reinforcement learning plays a role in training agents to take actions in certain environments. And this paper I found particularly interesting because it's adopting a form of reinforcement learning called MAML, model agnostic meta learning, which was a paper I've mentioned, I think, before in previous episodes. It came out around 2017 area and dealt with training reinforcement learning to optimize an inner and outer loop of an algorithm. So the idea is, can I train a model to be good at learning? So the example given in the original research paper was if I have some neural network and I want it to be efficient at taking a minimum number of gradient steps necessary to fine tune on a new data set, can I find that sort of optimal loss basin where the generalization to different fine tuning tasks is small? And so it consists of a dual inner and outer loop. But I'll cover a little bit more about that as we go through the paper. The paper itself is not a direct proper application. I don't want to say proper, but not a true to the original MAML application use of meta learning, but it is in the spirit of meta learning. And they present a agent training framework that optimizes two components, or they introduce two components into this meta learning framework. So one is a cross-episode training framework, and the other is in-context policy adaptation via prompt-induced reflection. So I'll cover each of these, what I mean by each of those as we go through the paper. They train it on two different language models, Quinn 3B and Llama 8B, and they train it on a few different agent benchmarks, including Minesweeper benchmark. There's another benchmark that sort of allows a language model to take actions, pushing crates sort of through a maze to solve them. And then there's a benchmark, more traditional agent benchmark that requires you to take a series of actions to make a purchase in a web environment. The last benchmark they test on is this pretty neat one where you have sort of a visual 3D environment, and the language model has to provide actions that need to be taken in the environment to discover different objects and accomplish different goals. So all of them sort of are algorithms, or environments that can be solved using traditional reinforcement learning algorithms. But the idea is, can we optimize a language model to be able to rapidly learn these environments rather than training a reinforcement learning model from scratch? So the paper kicks off by discussing the trade-off between exploration and exploitation, which is sort of the central tension in reinforcement learning. What weight do I give to trying unknown actions versus exploiting my current knowledge base to take obvious next actions, which I know are likely to lead to some reward? And obviously, there's been a ton of work into reinforcement learning in general. They make the comment that agents can tend to myopically hone in on a specific trajectory and sort of repeat actions, which I've seen personally deploying agents in production environments. And they want to be able to balance this exploration and exploitation in a RL training environment tailored to language modeling. They have a few introductory plots in the paper, which I won't spend too much time on, but the central idea is traditional reinforcement learning can cause a model to collapse into a certain trajectory, sort of inadvertently choosing to exploit where it should learn to explore in new environments. And they show some plots illustrating that their new algorithm provides a much more diverse way to explore an environment. The key design structure of this framework is multi-episode structure. So the algorithm learns in context, and it does that using this multi-episode structure, which is sort of a departure from the normal RL training loop that you'd see in a normal agent training environment. They mention some related work. LLM as an agent. Obviously, there's been a lot of research into agentic AI, some more template-based prompting techniques like React agents, where it's just sort of reflecting and then choosing an action. And there are some other research papers that use template optimization, where they have an agent verbally reflect on a last episode and maintain a reflection buffer going forward. And then in their related research section, they also mention meta reinforcement learning and reasoning. So reasoning is just the obvious kind of chain of thought thing that's taken off in the last year or so. And meta reinforcement learning is the version of mammal that I described a few minutes ago. They call out that this isn't, like I mentioned, a true mammal application where, mammal has some computational difficulty and requiring calculation of second order derivatives and things like that. But they do a sort of similar thing in the spirit of mammal, where they have an outer loop and an inner loop that's sort of training a model to be able to train, so to speak. It is interesting, the thought that you could extend a few-shot learning environment to a language model setting. So I'm sure many people are familiar with few-shot learning. Like if you're going to perform inference on a model, you can provide a few examples in the prompt template or the context, and then provide a new example that you want it to solve. And the fact that it has seen those previous examples prior to solving the newest one oftentimes improves the performance overall, because it sort of starts to understand the needed structure and answer template. And you could think about extending few-shot learning into the realm where you can learn entire algorithms in the few-shot examples given. So if you think about like the Minesweeper test environment they use here, Minesweeper being the classic Windows game we all played as kids, where you kind of click around on a little grid, and if you click the wrong grid coordinate, you can explode a mine, and you have to kind of flag all the mines, and then once you've solved it, then you win the game. If you could provide few shot examples of choosing actions in a Minesweeper environment and sort of concatenate those together, including historic failures and where you may have been able to improve previously, and then now ask it to solve a new blank slate Minesweeper game. If it's possible, then in some sense that it's optimized an internal reinforcement algorithm simply within its own context window. This would of course be transient. As soon as you create a new environment, and don't have that prompt template anymore. It doesn't know the algorithm anymore, but the fact that it's able to learn this algorithm in this context would be compelling. Potentially applications in other areas of machine learning, standard classification tasks. It would be an interesting field to kind of probe a bit further. So they get into the preliminaries. I'll lay out their solution framework. It's just a standard reinforcement learning or Markov decision process framework. So you have some set of states, some set of actions that you can take, some transition distribution. So, given that you're in some state and you take some action, the environment transitions you to the next state according to some distribution. And then you have the standard rewards. And you also have some sort of discount factor for how heavily or not heavily you want to weight certain rewards close to the end or far away from the end of the episode. They denote a trajectory as tau or an episode. So within this episode, you just have the standard tuple of state, action, reward items, and you have some number of these tuples for the number of steps that occurred during the episode. They take an episode up to time step t, and then you're optimizing the expectation value of the reward over these time steps within the episode, again weighted by this discount factor, which is somewhere between 0 and 1. So again, just the standard RL setup. So this is where they start to introduce some of their unique framework. So again, their framework consists of two components. So they change the way that they're constructing rewards, in that in a normal reinforcement learning environment, you can perform your rollouts, advantage computation, and log prob loss computation in parallel, and you can do this because during your rollouts, let's say you start at some state and you use your policy to roll out some number of state action tuples through the episode until it terminates. You have to do this in times, K rollouts, for example. And then once you have those K rollouts, you can calculate advantages however you want, GAE or some GRPO style advantage. But regardless, the rollouts themselves are independent. So one rollout episode doesn't have to precede the next one. They change that here, so you lose the ability to parallelize your rollouts. But the reason they do that is because they want to simulate this sort of in-context learning environment that they are optimizing for. So in this framework, Lamer framework, you generate some number of episodes, up to N episodes. Each episode is sequentially generated. So we generate episode 1, rollout 1, then we generate rollout 2, then 3. And the reason we do this is because the results of rollout 1 inform rollout 2, or 0 and 1 if you're zero indexing. So the reason they do this is because they use some best practices synthesized using a kind of prompt template from the first episode going into the second. So I'll talk more about that in a minute, but the first portion of the algorithm they talk through in depth is this cross-episode training framework. Let's first think about a single episode of a rollout. So a single episode of a rollout, we can calculate some discounted reward for this episode. So let's say for the episode N, we have some sum from the current time step to the end of time of the episode, the max number of time steps. And we have this gamma weight factor that provides some exponentiated weight to the reward received at this specific time step we're summing over. So you have, a sum of time steps from the current time step plus the next one, et cetera, to the end of the episode. Each one is weighted by this factor. And in this case, they call it a gamma step. And this is the within episode discount factor. So within this specific rollout, how much do we want to discount the reward? So that's that's like a standard RL setup. So that's nothing new at this point. But when they construct their objective, they change that a little bit. So they choose their discounted return as not just the return discounted within the episode, but also the return discount across episodes. So for any specific episode we take the total discounted reward for this episode is the discounted reward, the standard one, which we just discussed. That's just the discounted reward until the end of this current episode. But we also include a weighted sum of the discounted returns from previous or future episodes. And that's sort of where this cross episode framework comes in. So you're not just weighting the reward gotten in the current episode, you're also including a sum over rewards gotten in previous episodes. And they introduce a second constant here, gamma TRAJ, trajectory, traj, which is also between 0 and 1, but it's what they call the cross-episode discount factor. And this gamma provides you some ability to trade off between exploration and exploitation. They call out that a small trajectory gamma biases the objective towards early episodes and leads to rapid exploration, as opposed to the opposite, doing more exploration at the early stage. So this is, again, in contrast to a standard reinforcement learning setup where rollouts can be generated in parallel because they're independent. Here, because we need to calculate rewards across episodes, and also because we have to include summarized outputs, which I'll talk about more in a minute, from episode N-1 in episode N, we have to generate these sequentially. Okay, so the second part of their contribution here is what they call in-context policy adaptation and self-reflection. I'll just quote the paper here directly. Specifically, after each episode finishes, we prompt the agent to generate a textual reflection of the previous attempt, providing feedback and a plan to guide the next episode. So your policy for the current time step is parameterized by the episode number, where you have this, they call it H sub N, where N is your episode number, and H is this sort of summarized prompt template. So they provide the prompt template used to generate this, but basically it's like thinking of it like, so we generate episode 1, let's say we fail, and it's because we took a left at fork number 1 instead of a right in solving a maze. That episode is fed into a meta LLM, sort of an outside judge or summarizer, and the outside judge provides like a best practice, let's say. And that best practice goes into the prompt template that's used to generate episode 2. So you sort of have 2 layers of things going on here. One is the cross-layer reward discount, cross-episode reward discount, and this is what I mentioned. Your episode's reward isn't just the reward within the episode, but it's also including the sum from previous and other episodes in your rollout. And you also have this prompt template that's kind of growing in probably length, but also information density over the number of they provide some generalized framework for optimizing this setup. It's sort of what you would expect. You just have some sum over time steps and episodes. You have your standard gradient of your log probabilities of the actions, or in this case, we'd be like token level. The actions generated by your policy, where your policy has been conditioned on this H template. You can calculate advantages as well. They don't provide a specific breakout or formula for the advantage here because the framework is generalizable. So using this framework, you could apply any existing standard policy gradient algorithm. And they do, in fact, that later in the paper. They include PPO, GRPO, and a few other variants of popular RL approaches. But the point of providing this generalized objective in the theoretical layout is that it's just a template. The real secret sauce in the approach is using this iteratively improving prompt template generated using reflection on the previous episode, as well as this cross-episode reward discount. Okay, so that's the full theory of the paper, kind of like a little bit less theory than some of the other papers we've discussed, but I think a pretty powerful framework, and really interesting to see meta-learning start to make a comeback in some of the tasks here. I think it's particularly interesting for fine-tuning models, learning quickly in environments. In the experimental details section, they do some ablations on different values for the gamma step and gamma trajectory. They also try a couple of different models, specifically Llama 3.18b Instruct, and Quinn 3.4b is the base model for all their experiments. They call out the testing environments here: Alf World, Minesweeper, Web Shop, and Sokoban. Again, these are sort of RL-esque frameworks. Two of them are sort of gamified environments with a goal state, or sort of a similar goal state across episodes. The other two are more standard agentic benchmarks where you have to choose the right shirt to buy or navigate through a room to find an apple sort of thing. So varying goals that can be taken within an environment. They compare their method with pass at 1, pass at 2, pass at 3. So what's interesting here is at least not theoretically, the performance shouldn't necessarily be better in a zero-shot environment or a one-shot environment because it doesn't have this prompt template it's building up over time, and it would presumably be exploring more in the earlier attempts at the solution versus some of the later episodes. Anyways, however, they do show that they have a pretty strong pass at 1 rate compared to some other techniques, which are some of the prompting based techniques, which are like React, reflection. Reflection is just kind of using like a naive summary over past attempts at the solution. They also include their methods combined with other RL frameworks like PPO, RL, OO, GRPO, and GI, GPO. It would be interesting to see a PPO loop variant, which was a RL variant that came out that was pretty successful in the App World benchmark not too long ago. But nonetheless, they show that their pass at 1, 2, and 3 rate for these different benchmarks outperforms the standard approaches to solving these benchmarks. Again, later they provide some ablations for different gammas. One thing that I did find interesting is that they use 2 different forms of this cross-episode prompt template. One of them, they only include reflections. So like this would be like you take your historic set of episodes, put them into an LLM, and it provides some set of best practices to use during your next rollout. They also include trajectories, so like the raw trajectory data, and they try two different versions of H. One is three different versions, I should say. One is only using the trajectories from the previous episodes, so no summarized reflection. The other version uses only the summarized reflection, and then another version uses both the summarized reflection and the historic trajectories. The trajectories alone pretty significantly underperform the other variants in both situations. The reflection only, interestingly, provides the best performance as opposed to providing a reflection as well as historic episodes. They provide some idea for this is because reflection-only memory presents more concise and focused guidance, so possibly less noise for the model to sort through in its few shot context. I'll call out a few potential drawbacks to this approach. One of them is you have to generate your rollout sequentially, so that can increase your train time a lot longer. Also, your context window can grow pretty rapidly. So if you have a more complex reinforcement learning environment, including past trajectories into this H, or even just the reflections into this H, could increase the size of the context window needed to be able to generate a rollout. So you could be precluded to long context window models. It would be interesting to look at intersections of this with state space modeling or recurrent models where you don't have such a hard cutoff on the context window. But nonetheless, I think it is a pretty interesting alternative approach to training some of these agents. I think the other potential thing that stood out to me is in coming into a new environment, unless you were to sort of like save a prompt template or something like that, it does take a few. It would potentially take a few shots to learn a new environment or learn a new task. So there could be some trade-offs there. If you're at some sort of benchmark where you have to have one-shot performance on things, this method could potentially struggle. But again, I think it's a really cool approach, an application of pseudo-mammal, I'll call it, into RL-based agentic training pipelines. And that kind of brings us to the end of the paper. It's, again, just a 10-page paper. It's a fairly straightforward read. They provide a nice layout of results and ablations and a fairly straightforward to read theory section. So again, I'll put the link to the paper in the episode description. And thanks again for listening. Again, I'm your host, Aaron, and I'll be choosing research papers to walk through in future episodes. If you have any requests, feel free to drop in the comments or email me, Aaron at frankenstein-ai.com. And other than that, I hope you have a good rest of your week, and I'll talk to you next time.